In the Chapter 5, Part 2A video, we talked about solutions. And we said that solutions consist of at least one solute and also a solvent. The solvent is the component that does the dissolving, and the solute is the component that gets dissolved. So now we're going to take a deeper look at solutes. A solute can be either a molecular compound like a sugar or an alcohol, or a solute can be an ionic compound. We also call ionic compounds salts, like sodium chloride, for an example, is a solute that's dissolved in salt water. And so we call the salt water a sodium chloride, which is NaCl, a sodium chloride solution. And so ionic compounds, of course, are composed of ions. And so when you put a solid salt like sodium chloride in water, of course, in the liquid state, those ions that make up the salt will separate from each other and therefore get dissolved in the water. We learned that water is polar. It has an overall permanent dipole. And that dipole means that the oxygen, being more electronegative than the hydrogen, the oxygens carry a partial negative charge and the hydrogens carry a partial positive charge. So when you put the salt in the water, those ions, the Na plus ion and the Cl minus ion, they separate from each other and get dissolved in the water. What causes them to be dissolved in the water is that the +1 charge of the sodium is going to be attracted to the partial negative charge on the oxygen of the water. The -1 charge chloride ions are going to be attracted to the partial positive charge on the hydrogen atoms of water. And so this type of interactions between the ions of the dissolved salt and the partial negative and partial positive charges on a water molecule, those black dashed lines that you see, these are called ion-dipole interactions. These are intermolecular forces. Just like hydrogen bonds that we talked about earlier, we classified hydrogen bonds as a type of intermolecular force. Well, these ion-dipole interactions can also be considered a type of intermolecular force. So if your salt or your ionic compound consists of a polyatomic ion instead of a monoatomic ion like the chloride ion in NaCl, sodium chloride, what if we have a salt like sodium sulfate? Well, sodium sulfate is composed of the polyatomic ion sulfate. So when that salt dissolves in water, that polyatomic ion stays full and intact. The sulfur does not separate from the oxygens in that polyatomic ion. It stays as a full intact polyatomic ion. So you get 3 total separate ions for every unit of sodium sulfate that dissolves. You get 2 Na plus ions, and you get 1 sulfate polyatomic ion. So do all ionic compounds that exist, do they all dissolve in water? No, they do not. Most do, but some do not. So this is our solubility rule table. This table tells you whether or not a particular ionic compound will be soluble in water. That means it will dissolve in water. Or if it is insoluble, meaning that it will not dissolve. So soluble means yes, the salt will dissolve in water. Insoluble means that it will not. And so on the far left, this column tells you the type of ions. And if this type of ion is a part of the salt, then the rule will tell you whether or not that particular salt will be soluble or not soluble. So for example, if a salt contains a group 1 metal, the group 1 metals include lithium, sodium, potassium, rubidium, cesium, and francium. So if an ionic compound contains one of those group 1 metals, or if it contains the ammonium polyatomic ion, then that salt will be soluble. No exceptions. If your ionic compound contains a nitrate polyatomic ion, then that ionic compound will be soluble. No exceptions. If your ionic compound contains a chloride ion, or for that matter, a bromide ion, an iodide ion, so here we'll say in general the halides. Chlorides, they're one type of halide. So we'll include all of the halides, which are pretty much all of the group 7A nonmetals. With the exception of fluoride. And so if your ionic compound contains one of these monoatomic ions, which we call halides, bromide, iodide, chloride, then that ionic compound, most of them will be soluble. There are some exceptions. These are the exceptions. If the halide monoatomic anion is paired with a silver cation, Ag+, a mercury 1 ion, Hg+, or lead 2, Pb2+, then that ionic compound will be insoluble. So for example, silver chloride contains that silver Ag+ ion. So therefore, silver chloride is insoluble. However, magnesium chloride is soluble because it's paired with a magnesium cation, which is not one of the exceptions. If an ionic compound contains a sulfate polyatomic ion, SO4 2-, then most of them are soluble, and there are, again, some exceptions. These are the exceptions. If an ionic compound contains a carbonate polyatomic ion, CO3 2-, then more than likely it will be insoluble. But there are a couple of exceptions. These exceptions would make the ionic compound soluble, whereas the other two rows above this one, those exceptions means that if they're in the ionic compound paired with a halide anion or a sulfate polyatomic anion, then the ionic compound will be insoluble. The exception here, if a carbonate polyatomic anion is paired with a group 1 metal like lithium or potassium or sodium, or if it's paired with the ammonium NH4 plus polyatomic cation, then the ionic compound will be soluble. And then finally, the hydroxides, the OH minus polyatomic ion, and sulfides, the S2 minus monoatomic anion. If an ionic compound contains either of these anions, then they'll be mostly insoluble, not soluble. And again, the only other exceptions that would make an ionic compound soluble if it contains a hydroxide anion or a sulfide anion is if it's paired with a group 1 metal cation, like sodium +1 or potassium +1, or the ammonium polyatomic cation, NH4 plus. Now, when two ionic compounds react, they do so by a type of reaction we saw in one of our labs earlier in the semester that we call a double displacement reaction, which means that you're changing partners or exchanging ions. So the ionic compounds will exchange ions with each other. When this type of double displacement reaction, which we also call a precipitation reaction, if one of the products is a solid, it's just simply a double displacement reaction if both of the products dissolve in water and therefore form aqueous solutions. But if one of the products is a solid and the other product is an aqueous solution, then we call the double displacement reaction a precipitation reaction. So for this example, you've got silver paired with the nitrate polyatomic ion, giving you silver nitrate. And when I do these reactions, I like to put the charges on my ions so that when they switch partners, I'll know which charge that they'll have when they're now a new product with a new ion partner. So the silver is going to break up with the nitrate, and it's going to get a new negative ion partner, the chloride ion. And so by using my charges, I'm ensuring that I'm writing my ionic compound formula correctly. So silver stole the sodium Na+'s partner, the chloride ion. So now the sodium is lonely and needs a new partner. And the nitrate got kicked out by the silver. So now the sodium and the nitrate are going to pair up. The plus and the -1 ion charges on the silver and the chloride cancel each other out. So I wrote that formula correctly. The sodium +1 charge gets canceled out by the nitrate's -1 charge. So I wrote that formula correctly as well. So now that I've written my formulas, I can remove the charges. So now I've got to decide, is silver chloride a solid, meaning that it didn't dissolve in water? Or did it form an aqueous solution, meaning that it dissolved in water? How do I know? I go to my solubility rules. So I've got a halide. That chloride is a halide. So I go to my halide rules. And it says they're mostly soluble, except if they're paired with a silver, a mercury, or a lead. So the exception rules. So that means silver chloride is insoluble. So this is a solid. If it's insoluble, that means it's not an aqueous solution. It forms a solid. My NaNO3, NO3 is the nitrate polyatomic ion, so I follow my nitrate rule. All nitrates are soluble, no exceptions. So if it's soluble, it forms an aqueous solution. Ionic compounds are called salts. They are also called electrolytes because they're able to form a solution when they dissolve in water. Their ions separate, those ions get dissolved in the water, and those ions are free to move. So in being free to move, those ions have the ability to conduct an electrical current. So ionic compounds are electrolytes. Salts are electrolytes. Its opposite, sugars. Sugars are made of molecules. Ionic compounds are made of ions. So therefore, because sugars are made of molecules, they don't form any ions in solution. So they are non-conducting. They cannot conduct an electrical current, and they are called non-electrolytes. So if you dissolve NaCl in water, it's conducting. It's an electrolyte. And therefore, if you place electrodes in a salt solution, it conducts an electrical current and the light bulb comes on. And it's very bright. And the reason why it's so bright, because NaCl is not just an electrolyte, it's a strong electrolyte. A sugar solution placed with electrodes placed in it, the light bulb does not come on. Because there are no free ions in solution, because the sugar does not contain ions. So therefore, a sugar solution can't conduct an electrical current. So I mentioned that ionic compounds are strong electrolytes because they dissociate completely into ions in water. In addition to ionic compounds being strong electrolytes, so are strong acids and strong bases. If a compound partially dissociates into ions in water, it's called a weak electrolyte. Weak acids and weak bases, as well as tap water, are considered weak electrolytes. Non-electrolytes do not contain ions at all. And so therefore, they cannot conduct an electrical current at all. Weak electrolytes can weakly conduct an electrical current. So if we had another picture here where if an NaCl solution was replaced with tap water, then the light would still come on, but it wouldn't shine as bright. It would be a very, very faint light that would appear. Whereas with a strong electrolyte, the light bulb comes on, it's very bright. But with a weak electrolyte like tap water, the light would come on, but it wouldn't be as bright. Non-electrolytes, however, like sugars, alcohols, purified water that's been deionized or distilled, those are all non-electrolytes, and they cannot conduct an electrical current at all. Also, any ionic compound that is non-soluble is also considered a non-electrolyte. And so if you have a solution of two liquids, so a liquid plus liquid solution, then whether or not the two liquids will mix in each other and therefore be miscible in each other will depend on if they like each other or not. So the rule is like dissolves like. And so, meaning that the two liquids have to have the same polarity. So two polar liquids will dissolve in each other. For example, ethanol and water are both polar, and so they will dissolve in each other. Nonpolar compounds like oil will dissolve in other nonpolar compounds like gasoline. But if you try to dissolve oil in water, they will not be miscible in each other. They're called being immiscible in each other because oil is nonpolar and water is polar. They are not the same type of liquids, so they will not dissolve in each other. So looking at this table, we have ionic compounds. So we provide the names. And lead is a compound, is a metal cation that can either have a 2+ or a 2- charge. Paired with nitrate, the nitrate polyatomic ion has a -1 charge. So therefore, having two of them in the formula, you balance out the -2 charge. So lead has to have a +2 charge. So this is lead 2 nitrate. The next one is calcium. Sulfate. Calcium is not a transition metal, nor does it have more than one type of charge as a cation, so no Roman numeral is necessary. Aluminum is also not a transition metal. It's a group 3A metal. So this is aluminum hydroxide. OH is the hydroxide polyatomic ion. And then we have the transition metal silver. So that's silver 1 bromide. So are these soluble or insoluble in water? So we'll answer these yes, no. Is it soluble in water? So lead nitrate, the nitrate solubility rule, all nitrates are soluble, no exceptions. So yes, lead nitrate is soluble in water. Calcium sulfate, let's look at the sulfate rule. Sulfates are mostly soluble unless they're paired with a strontium metal, a barium metal, a lead 2 metal, or a silver 1 metal. So calcium sulfate, yes, is soluble. It doesn't meet any exception. Calcium is not one of those exceptions for sulfate. And then aluminum hydroxide. Hydroxides rule, they're mostly insoluble unless the hydroxide is paired with a group 1 metal or an ammonium cation. Aluminum is not a group 1A metal and is definitely not the NH4+ polyatomic cation. So therefore, aluminum hydroxide is not soluble. Silver bromide, you look at the bromide or the halide rule. There's bromide. Mostly soluble except for if it's paired with silver, mercury, or lead. AgBr is paired with silver. It meets that exception, so it is not soluble. The next question, We're writing balanced equations for these reactions between two ionic compounds. And then we need to decide whether or not a solid precipitate will form. Basically, we need to decide if one of the ionic compound products is insoluble or not, and therefore it will form a solid precipitate if it is insoluble. So NaS paired with MgCl2 will switch to partners. So sodium is a group 1, sulfur is a group 6A, so it has a -2 charge. Magnesium has a +2 charge. Chloride has a -1. So sodium is going to now pair up with chlorine, and magnesium is going to pair up with sulfur. Looking at our solubility rules, sodium chloride. Sodium is a group 1 metal. Group 1 metals are all soluble, no exceptions. So this will be an aqueous solution because it's soluble. Magnesium sulfide. We'll look at the sulfide rule. Sulfides are mostly insoluble, except for if they're paired with a group 1 metal or NH4+. Well, magnesium is not a group 1 metal. It is a group 2 metal. So this will be insoluble, and therefore MgS, being insoluble, will be a solid. So this is our precipitate. And therefore, A is a precipitation reaction. The next one, copper nitrate, reacting with NaCl. They're going to switch partners. And in this, you see the nitrate polyatomic ion has a -1 charge. There's 2 of them, so total -2. So copper has to have a +2 charge to balance out the -2. So we're dealing with copper 2. Copper is going to get a new partner, the chloride ion. So we've got to have 2 chloride ions to balance the +2. And I'm going back to A to balance my reaction. We needed a 2 to be in front of the NaCl so that we have 2 sodiums and 2 chlorine atoms on each side of the arrow. And then sodium's new partner is going to be the nitrate polyatomic ion. Their charges already balance out. So I've written my formulas correctly. So now I'm going to go ahead and just remove those charges. So now that I've got my reaction written, now I'm going to balance it. I need 2 nitrates on each side of the equation, and I need 2 chlorines on each side. I've got 2 on the right, so I'm going to put a 2 here, so I have 2 on the left. Now I've got 2 sodiums on the left, put a 2 here to have 2 sodiums on the right. And now in doing that, I've got 2 nitrates on both sides. So now my reactions balance. Now I've got to decide if one of these products is a precipitate or not. So I've got a chloride and a nitrate. Well, one of the rules says that all nitrates are soluble, no exceptions. So my nitrate salt will be soluble. So that's an aqueous solution. Now looking at my chloride, that's a halide. They're also mostly soluble, with the exceptions of silver, mercury, and lead. Well, copper is not silver, mercury, or lead, so this guy is also going to be soluble. So this is not a precipitation reaction. This is just simply a double displacement. It's not a special class of double displacement called a precipitation reaction because neither of the products are solids. Looking at the third one, AgNO3 reacting with KCl. They're going to switch partners. We write in my charges, so they're all plus ones and minus ones. So it's an easy reaction to write. All nitrates are soluble. Just like sodium nitrate is an aqueous solution, so is potassium nitrate. And then our chlorides, we've got AgCl. And for our chlorides, they're all mostly soluble, except for silver, mercury, lead paired with the chloride. So with the silver being paired with the chloride, that's going to be one of our exceptions, and that's going to make that a solid. So this is a precipitation reaction because one of the products is a solid. And the last question, identify the following as either a strong electrolyte, weak electrolyte, or a non-electrolyte. Glucose is a sugar. 1-propanol is an alcohol. These are both non-electrolytes. KNO3 is a soluble, all nitrates are soluble. So it's a soluble ionic compound. So that means it's a strong electrolyte. Tap water is a weak electrolyte. Dasani bottled water is purified water. So that makes it a non-electrolyte. HCl is a strong acid. That makes it a strong electrolyte. Acetic acid is a weak acid. And that makes it a weak electrolyte. And that brings us to the end of the Chapter 5, Part 2B pre-class lecture.